What do you understand by climate? Climate is the general weather over a long period. This can include rainfall, temperature, snow, or any other weather condition. We usually define a region's climate over a period of 30 years. Climate is the average weather conditions in a specific area over an extended period of time. A climate description typically includes data on various factors such as the average temperatures during different seasons, precipitation levels, and the amount of sunlight. Climate, conditions of the atmosphere at a particular location over a long period of time. It is the long-term summation of the atmospheric elements, and their variations, that, over short time periods, constitute weather. These elements are solar radiation, temperature, humidity, precipitation, type, frequency, and amount, atmospheric pressure, and wind, speed and direction. The Köppen climate classification is one of the most widely used climate classification systems. It was first published by German-Russian climatologist Vladimir Köppen, 1846–1940, in 1884, with several later modifications by Köppen, notably in 1918 and 1936. Later, German climatologist Rudolf Geiger, 1894–1981, introduced some changes to the classification system in 1954 and 1961, which is thus sometimes called the Köppen-Geiger climate classification. The Köppen climate classification divides climates into 5 main climate groups, with each group being divided based on patterns of seasonal precipitation and temperature. The 5 main groups are A, tropical, B, arid, C, temperate, D, continental, and E, polar. Each group and subgroup is represented by a letter. All climates are assigned a main group, the first letter. All climates except for those in the E group are assigned a seasonal precipitation subgroup, the second letter. For example, AF indicates a tropical rainforest climate. The system assigns a temperature subgroup for all groups other than those in the A group, indicated by the third letter for climates in B, C, D, and the second letter for climates in E. For example, CFB indicates an oceanic climate with warm summers as indicated by the ending B. Climates are classified based on specific criteria unique to each climate type. Solar radiation and temperature. Air temperatures have their origin in the absorption of radiant energy from the sun. They are subject to many influences, including those of the atmosphere, ocean, and land, and are modified by them. As variation of solar radiation is the single most important factor affecting climate, it is considered here first. Nuclear fusion deep within the sun releases a tremendous amount of energy that is slowly transferred to the solar surface, from which it is radiated into space. The planets intercept minute fractions of this energy, the amount depending on their size and distance from the sun. A 1 square meter, 11 square foot, area perpendicular, 90 degrees, to the rays of the sun at the top of Earth's atmosphere, for example, receives about 1,365 watts of solar power. This amount is comparable to the power consumption of a typical electric heater. Because of the slight ellipticity of Earth's orbit around the sun, the amount of solar energy intercepted by Earth steadily rises and falls by plus or minus 3.4% throughout the year, peaking on January 3, when Earth is closest to the sun. Although about 31% of this energy is not used as it is scattered back to space, the remaining amount is sufficient to power the movement of atmospheric winds and oceanic currents and to sustain nearly all biospheric activity. The solar constant, GSC, measures the amount of energy received by a given area 1 astronomical unit away from the sun. More specifically, it is a flux density measuring mean solar electromagnetic radiation, total solar irradiance, per unit area. It is measured on a surface perpendicular to the rays, 1 astronomical unit, O, from the sun, roughly the distance from the sun to the Earth. Earth's atmosphere is heated up because of the following 3 important processes. They are: conduction. It is a process in which heat flows from objects with higher temperatures to objects with lower temperatures. The air in contact with the land gets heated gradually and the upper layers in touch with the lower layers also get heated. Convection. Vertical heating of the atmosphere is known as convection. The air in contact with the Earth upsurges vertically on heating in the form of currents and transfers the heat of the atmosphere. Advection. The transfer of heat through the horizontal movement of air is called advection. About 29% of the solar energy that arrives at the top of the atmosphere is reflected back to space by clouds, atmospheric particles, or bright ground surfaces like sea ice and snow. This energy plays no role in Earth's climate system. About 23% of incoming solar energy is absorbed in the atmosphere by water vapor, dust, and ozone, and 48% passes through the atmosphere and is absorbed by the surface. Thus, about 71% of the total incoming solar energy is absorbed by the Earth system. The atmosphere and the surface of the Earth together absorb 71% of incoming solar radiation, so together, they must radiate that much energy back to space for the planet's average temperature to remain stable. However, the relative contribution of the atmosphere and the surface to each process, absorbing sunlight versus radiating heat, is asymmetric. The atmosphere absorbs 23% of incoming sunlight while the surface absorbs 48%. The atmosphere radiates heat equivalent to 59% of incoming sunlight, the surface radiates only 12%. In other words, most solar heating happens at the surface, while most radiative cooling happens in the atmosphere. Albedo, derived from the Latin word albedo, which means whiteness, refers to the proportion of sunlight that is diffusely reflected by an object or surface. It is typically quantified on a scale ranging from 0, representing a black body that absorbs all incoming radiation, to 1, representing an object that reflects all incoming radiation. In other words, albedo measures how much of the sunlight that strikes an object is bounced back or reflected rather than absorbed. Diffusion is the net movement of anything, for example, atoms, ions, molecules, energy, generally from a region of higher concentration to a region of lower concentration. Diffusion is driven by a gradient in Gibbs free energy or chemical potential. It is possible to diffuse uphill from a region of lower concentration to a region of higher concentration, as in spinodal decomposition. Diffusion is a stochastic process due to the inherent randomness of the diffusing entity and can be used to model many real-life stochastic scenarios. Therefore, diffusion and the corresponding mathematical models are used in several fields beyond physics, such as statistics, probability theory, information theory, neural networks, finance, and marketing. The temperature of the air at a given location is influenced by several factors, including 1. Latitude of the place. Generally, areas closer to the equator, lower latitudes, tend to have higher temperatures, while areas closer to the poles, higher latitudes, have lower temperatures. 2. Altitude of the place. Temperature decreases with increasing altitude. As you move to higher elevations, the air becomes cooler. 3. Distance from the sea. Coastal areas often have milder and more stable temperatures compared to inland regions. Oceans have a moderating effect on temperature, so coastal areas experience less temperature variation. 4. Air mass circulation. The movement and circulation of air masses, which can be influenced by global wind patterns, affect temperature. For example, winds blowing from polar regions may bring colder air, while winds from equatorial regions may bring warmer air. 5. The presence of warm and cold ocean currents. Ocean currents can transfer heat across large distances, affecting the temperature of coastal regions. Warm ocean currents tend to raise temperatures, while cold currents can have a cooling effect. 6. Local aspects. Local geographical features, such as mountains, valleys, and bodies of water, like lakes, can create microclimates within a region. These local aspects can significantly impact temperature variations in specific areas. These factors interact and combine to determine the overall climate and temperature characteristics of a particular location. The incidence of solar rays, or insolation, on a specific location is influenced by various factors, which include 1. Shape of the Earth. The Earth's spherical shape affects how sunlight is distributed across its surface. This shape leads to variations in the angle of incidence of sunlight, with higher latitudes receiving sunlight at a more oblique angle, leading to lower temperatures. 2. Axis obliquity and annual movement, seasons. The tilt of the Earth's axis and its orbit around the Sun result in the changing seasons. The angle and duration of sunlight vary throughout the year, impacting temperature and climate. 3. Daily movement. The Earth's rotation on its axis causes the Sun to appear to rise in the east, move across the sky, and set in the west. This daily movement influences the diurnal temperature variation in an area. 4. Aspect and slope. The orientation, aspect, and angle, slope, of the land's surface affect how it absorbs and reflects sunlight. South-facing slopes receive more direct sunlight in the northern hemisphere, while north-facing slopes receive less. 5. Insolation duration. The length of daylight hours varies with latitude and the time of year, affecting the amount of solar energy a location receives. 6. Elevation. Higher altitudes generally receive more intense sunlight and experience cooler temperatures. This is why mountainous regions are often cooler than lowland areas at the same latitude. 7. Distribution of land and seas. Oceans have a moderating effect on temperature, and their large heat capacity stabilizes coastal climates. Land heats up and cools down more quickly than water. 8. Humidity. the presence of water vapor in the atmosphere can affect the absorption and retention of solar energy, leading to variations in temperature and climate. 9. Ocean currents. Warm ocean currents can transfer heat to coastal areas, influencing their climate. Cold ocean currents can have a cooling effect on nearby regions. 10. Wind. Wind patterns carry heat and moisture, impacting temperature and climate. For example, winds from the ocean can bring humid air to coastal areas. 11. Vegetation. The presence of forests, grasslands, or deserts can influence local climate. Vegetation affects the exchange of heat and moisture between the land surface and the atmosphere. These factors collectively determine the local and regional climate patterns and temperature variations experienced in different parts of the world. The angle at which sunlight, or solar radiation, strikes the Earth's surface has a significant impact on the amount of energy per unit area that is absorbed, and therefore, the temperature of a location. Here's how it works. 1. Steep sun rays. When the sun's rays are perpendicular, falling directly overhead, they are concentrated over a smaller area, which results in a higher energy input. This leads to warmer temperatures. This is why regions near the equator experience higher temperatures, because the sun is nearly overhead throughout the year. 2. Reduced incidence angle. As you move away from the equator and towards higher latitudes, the sun's rays strike the Earth's surface at a more oblique angle, especially during the morning and evening. This means that the same amount of solar energy is spread over a larger area. The oblique angle results in less heating and cooler temperatures. In addition to the angle of incidence, factors like the duration of daylight, presence of cloud cover, and local geography also influence the actual temperatures experienced in an area. The interplay of these factors is what creates the diverse climates and temperature variations around the world. The angle at which sunlight falls on the Earth's surface is determined by several factors, including 1. Shape of the Earth. The Earth is not a perfect sphere, it's an oblate spheroid. This means that the angle at which sunlight hits the Earth's surface varies with latitude. Near the equator, sunlight strikes more directly, while at higher latitudes, it strikes at a more oblique angle. 2. Axis inclination and annual movement. Seasons. The Earth's axis is tilted relative to its orbit around the Sun. This axial tilt, about 23.5 degrees, is responsible for the changing seasons. As the Earth orbits the Sun, the angle and duration of sunlight change, resulting in variations in temperature and climate during the year. 3. Daily movement. The Sun appears to move across the sky during the day due to the Earth's rotation. This daily movement of the Sun affects the angle at which sunlight reaches the surface. The Sun is highest in the sky around noon, resulting in the most direct and intense sunlight. 4. Aspect and slope. The angle at which sunlight strikes a surface also depends on the orientation, aspect, and slope of the terrain. Surfaces that face the Sun directly receive more sunlight, while shaded or sloped surfaces receive less. These factors collectively influence the angle of incidence of solar radiation, which, in turn, affects the amount of energy and heat received at different locations on Earth, contributing to the planet's diverse climate and weather patterns. The shape of the Earth and its curvature play a significant role in how the angle of the Sun's rays changes with latitude, and this has a direct impact on temperature. Here's how it works. 1. Near the equator. At the equator, where the Earth's diameter is greatest, the angle of the Sun's rays is nearly perpendicular to the surface. This means that sunlight is concentrated over a smaller area, leading to higher temperatures and a warmer climate. 2. Towards the poles. As you move away from the equator and closer to the poles, the Earth's curvature causes the Sun's rays to strike the surface at increasingly oblique angles. This results in the same amount of solar energy being spread over a larger surface area, which leads to cooler temperatures. The variation in the angle of solar incidence explains why regions near the equator tend to be warmer and experience less seasonal temperature changes, while areas at higher latitudes, closer to the poles, have more pronounced seasonal temperature variations and colder climates. This effect is a fundamental driver of the Earth's climate patterns and is a key factor in the distribution of different climate zones around the world. You're absolutely right. The Earth's axial tilt and its orbit around the Sun are responsible for the changing angle of the Sun's rays throughout the year, which in turn leads to the changing of seasons. Here's how it works. 1. Axial tilt. The Earth's axis is tilted relative to its orbit around the Sun. This tilt is approximately 23.5 degrees. This tilt is responsible for the seasons. When a hemisphere is tilted towards the Sun, it experiences summer, and when it's tilted away, it experiences winter. 2. Orbital movement. As the Earth orbits the Sun, different parts of the planet receive varying amounts of sunlight. During the summer solstice, the North Pole is tilted towards the Sun, and the northern hemisphere receives more direct sunlight, resulting in summer. Conversely, during the winter solstice, the North Pole is tilted away from the sun, and the northern hemisphere receives less direct sunlight, leading to winter. 3. Equinoxes. During the spring and autumn equinoxes, the Earth's axis is not tilted towards or away from the sun, and day and night are of approximately equal length. These are the transitional periods between summer and winter. This annual variation in the angle of sunlight leads to the changing of seasons, affecting temperature, day length, and weather patterns throughout the year. The same principles apply to the southern hemisphere but with opposite timing. When it's summer in the northern hemisphere, it's winter in the southern hemisphere, and vice versa. Indeed, the angle of the sun's rays changes throughout the day, and this daily variation plays a significant role in temperature differences between morning, evening, and noon. Here's how it works. 1. Morning and evening. During the early morning and late evening, the sun is closer to the horizon, and its rays have to pass through a thicker layer of the Earth's atmosphere. This makes the sunlight scatter more, which can create beautiful warm colors during sunrise and sunset. However, because the sunlight is more spread out and has to pass through more of the atmosphere, it's less intense, and temperatures tend to be cooler during these times. 2. Noon. Around noon, when the sun is at its highest point in the sky, its rays are more direct and have to pass through a shorter path in the atmosphere. This results in more concentrated and intense sunlight, leading to higher temperatures. Noon is typically the warmest part of the day. The daily variation in temperature due to the sun's angle is most pronounced in places with a distinct day-night cycle. Coastal regions, for example, tend to have smaller temperature fluctuations due to the moderating effect of the ocean. Inland areas, on the other hand, can experience more significant temperature swings between day and night. Understanding these daily temperature variations is essential for various aspects of life, from agriculture and weather forecasting to energy conservation and outdoor activities. Aspect, as you mentioned, refers to the orientation or position of a place or slope relative to the sun. It plays a crucial role in the local climate and can affect factors like temperature and vegetation. Here's how aspect influences the angle of the sun's rays and, subsequently, the local climate. 1. Solar incidence angle. The solar incidence angle is the angle at which the sun's rays strike the Earth's surface. This angle varies throughout the day and throughout the year. Aspect determines how steep or shallow this angle is at a particular location. 2. Influence on temperature. South-facing slopes or aspects receive more direct sunlight, especially in the northern hemisphere. This means they tend to warm up more quickly and can be warmer overall. In contrast, north-facing slopes receive less direct sunlight and can be cooler. 3. Influence on vegetation. Aspect also affects the types of vegetation that can thrive in a particular area. South-facing slopes may support different plant species than north-facing slopes due to the temperature differences and sunlight exposure. 4. Seasonal variations. The angle of the sun's rays changes with the seasons, and aspect interacts with this variation. In winter, south-facing slopes can be warmer and have less snow, while north-facing slopes may remain cooler and retain snow longer. 5. Human activities. People have considered aspect in land use and agriculture for centuries. Choosing the right aspect for planting crops, building homes, or setting up solar panels can optimize the use of solar energy and resources. In summary, aspect is an essential consideration in understanding local microclimates, ecological patterns, and land use planning. It's particularly important in regions with diverse topography and varying solar exposure. The aspect effect you described, where southern slopes in the northern hemisphere, NHS, and northern slopes in the southern hemisphere, SHS, receive the sun's rays more steeply, leading to overheating, is a significant factor in local climate and microclimate variations. This effect is a result of how the angle of solar incidence changes based on the orientation of slopes relative to the sun. Here's a bit more detail on the aspect effect in both hemispheres. 1. Northern Hemisphere, NHS. In the NHS, which includes regions north of the equator, south-facing slopes receive more direct sunlight and thus heat up more during the day. This aspect effect is particularly noticeable in areas with mountainous terrain. South-facing slopes are often warmer and may experience more intense evaporation, affecting local vegetation and climate. 2. Southern Hemisphere, SHS. In the SHS, which includes regions south of the equator, north-facing slopes receive more direct sunlight, leading to similar effects as in the NHS. These slopes tend to be warmer and may have different vegetation and microclimates. The aspect effect can be seen more strongly at higher latitudes because the sun's angle varies significantly throughout the day and year. Near the equator, the angle of solar incidence is nearly vertical, so the aspect effect is less pronounced. Overall, the aspect effect plays a crucial role in shaping local climates, especially in regions with varied topography. It influences temperature variations, vegetation distribution, and other microclimate characteristics. Understanding this effect is important for activities such as agriculture, land use planning, and ecological studies in these regions. Indeed, the aspect of a slope can significantly impact various environmental and ecological factors, including the angle of solar incidence, insolation time, temperature, and vegetation characteristics. Here's how it affects these factors. 1. Takes the sun's rays at a more right angle. South-facing slopes in the northern hemisphere, NHS, and north-facing slopes in the southern hemisphere, SHS, receive the sun's rays more directly. This means the rays come in at a right angle, leading to more efficient heating and solar energy absorption. 2. Insolation time is high. These slopes receive sunlight for a longer duration during the day. This extended insolation time can promote more photosynthesis and plant growth. 3. The temperature is higher. As a result of receiving sunlight at a right angle and for an extended period, these slopes tend to be warmer than their counterparts on opposite-facing slopes. 4. The vegetation time of plants of the same species is shorter. The warmer and sunnier conditions on slopes with direct sunlight exposure can affect the growing seasons of plants. In such areas, plants may have shorter growing seasons and different flowering and fruiting times compared to those on cooler, shaded slopes. It's essential to consider the aspect of slopes when planning land use, agriculture, or conservation efforts, as it can influence microclimates, plant communities, and the overall ecological balance of an area. Different slopes may support distinct ecosystems and species compositions due to these variations in sunlight and temperature. The angle of arrival of the sun's rays, influenced by the aspect of a slope, can have several implications for the environment and human activities. Here's how it affects these factors. 1. Timberline limit is higher. The timberline is the elevation at which trees stop growing due to harsh environmental conditions. On slopes with a favorable aspect, for example, south-facing in the northern hemisphere, where the sun's rays hit more directly and temperatures are higher, the timberline limit tends to be at a higher elevation. Trees can grow at higher altitudes because of the increased warmth and sunlight. 2. Agriculture upper limit is higher. For agriculture, the elevation at which crops can be successfully cultivated is influenced by factors like temperature and the length of the growing season. On slopes with a more favorable aspect, agriculture can be practiced at higher elevations due to increased warmth and extended growing seasons. 3. Snowline is higher. The snowline represents the elevation above which snow covers the ground for extended periods. On slopes with a favorable aspect, the snowline tends to be at a higher elevation because snow melts more quickly in sun-exposed areas, especially during the daytime. 4. Snow stays for a shorter time. As a result of the higher snowline and more direct sunlight, snow cover on slopes with a favorable aspect tends to persist for a shorter duration. This can be advantageous for activities like agriculture, construction, and transportation, as well as reducing the challenges associated with prolonged snow cover. 5. Settlements are denser. Historically, people have often chosen to establish settlements in areas with favorable aspects, such as south-facing slopes. The increased warmth and sunlight make these areas more conducive to human habitation, agriculture, and various economic activities. This can lead to denser population centers in such locations. The aspect of a slope is a critical factor in determining the suitability of an area for various purposes, including agriculture, forestry, and human settlement. Understanding how aspect influences microclimates and environmental conditions is essential for land use planning and resource management. The thickness and density of the Earth's atmosphere play a crucial role in determining how incoming solar radiation is absorbed and scattered. Here's how atmospheric thickness, density, influences the angle of incidence of the sun's rays. 1. Absorption and scattering. Solar radiation travels through the atmosphere before reaching the Earth's surface. During this journey, some of the radiation is absorbed by atmospheric gases, and some of it is scattered in various directions. The thickness of the atmosphere affects the amount of absorption and scattering that occurs. Thicker and denser atmospheres will absorb and scatter more radiation compared to thinner atmospheres. 2. Angle of incidence. The angle at which solar radiation enters the atmosphere is influenced by the location on Earth. Near the equator, where the sun is more directly overhead, the angle of incidence is nearly perpendicular to the surface. As you move toward the poles, the angle of incidence becomes more oblique. This change in the angle of incidence affects the amount of atmosphere the radiation must pass through. 3. Radiation path length. The path length of solar radiation through the atmosphere varies with the angle of incidence. When the sun is directly overhead, high angle of incidence, radiation has a shorter path length through the atmosphere. In contrast, when the sun is lower in the sky, low angle of incidence, radiation must pass through a thicker layer of the atmosphere. The longer the path length, the greater the potential for absorption and scattering. 4. Atmospheric effects. The atmosphere also scatters sunlight, particularly shorter wavelengths like blue and violet, which is why the sky appears blue. This scattering can further influence the distribution of radiation reaching the surface. 5. Variations by location and time. Due to the Earth's axial tilt and its elliptical orbit around the Sun, the angle of incidence varies by location and time of year. This variation in the angle of incidence contributes to seasonal temperature changes, as regions receive varying amounts of solar energy at different times of the year. In summary, the thickness and density of the Earth's atmosphere affect how solar radiation is absorbed and scattered as it passes through the atmosphere. The angle of incidence, which varies with location and time of year, determines the path length through the atmosphere. These factors collectively influence the distribution of solar energy at the Earth's surface and are key drivers of climate and weather patterns. Indeed, the amount and composition of greenhouse gases in the Earth's atmosphere play a crucial role in regulating the planet's temperature and energy balance. Water vapor is the most abundant greenhouse gas and plays a central role in the Earth's climate system. Here are some key points about the relationship between atmospheric thickness, greenhouse gases, and their impact on Earth's climate. 1. Greenhouse effect. The greenhouse effect is a natural process that allows the Earth to maintain a relatively stable and habitable temperature. Greenhouse gases in the atmosphere, such as water vapor, carbon dioxide, CO2, methane, CH4, and others, trap heat from the sun, preventing it from escaping back into space. This trapped heat warms the planet, making it suitable for life. 2. Water vapor. Water vapor is the most abundant greenhouse gas. It is primarily responsible for the natural greenhouse effect. Its concentration in the atmosphere varies with factors like temperature and humidity. Warm air can hold more moisture, so the amount of water vapor in the atmosphere tends to increase with rising temperatures. 3. Human activities. While water vapor is the dominant greenhouse gas, human activities have significantly increased the concentration of other greenhouse gases, such as CO2 and CH4, through activities like burning fossil fuels, deforestation, and industrial processes. These additional greenhouse gases contribute to enhanced greenhouse warming, leading to global climate change and increased average temperatures. 4. Atmospheric thickness. The thickness and density of the Earth's atmosphere decrease with altitude. The troposphere, the lowest layer of the atmosphere, contains most of the atmosphere's greenhouse gases. The density of these gases diminishes with increasing altitude, making the upper atmosphere less effective at trapping heat. 5. Albedo effect. In addition to greenhouse gases, the reflectivity of the Earth's surface, known as albedo, also influences climate. Surfaces that reflect more sunlight, such as ice and snow, have a cooling effect, while darker surfaces, like forests or oceans, absorb more heat. Changes in albedo, such as melting polar ice caps, can impact the Earth's energy balance and contribute to global warming. 6. Climate feedbacks. Changes in the concentration of greenhouse gases can trigger various climate feedback mechanisms. For example, as polar ice melts due to warming, it reduces the Earth's albedo, leading to more heat absorption and further warming. Such feedback loops can amplify the effects of climate change. Understanding the complex interactions among these factors is crucial for climate science. Efforts to mitigate climate change involve reducing the emission of human-produced greenhouse gases and understanding how changes in atmospheric composition affect our planet's climate and ecosystems. The contrast between marine, oceanic, and terrestrial, land-based, areas in terms of warming and cooling is influenced by various factors, including the presence of greenhouse gases and humidity. Here's a breakdown of the differences. 1. Greenhouse gases. Greenhouse gases, such as carbon dioxide, CO2, and water vapor, humidity, play a crucial role in trapping heat in the Earth's atmosphere. In terrestrial areas, the concentration of greenhouse gases can vary, and when there are fewer of these gases, warming and cooling can happen more rapidly. Land surfaces can heat up quickly under the influence of solar radiation, and they can also lose heat rapidly, leading to significant temperature fluctuations. 2. Marine areas. Marine areas, which include the open ocean, seas, and large bodies of water, have higher humidity levels and more consistent greenhouse gas concentrations, particularly water vapor. This high humidity acts as a thermal buffer, slowing down the warming and cooling processes. Water has a high heat capacity, meaning it can absorb and store a significant amount of heat without experiencing rapid temperature changes. As a result, marine areas tend to have milder and more stable temperatures compared to terrestrial areas. 3. Seasonal differences. The presence of water bodies moderates temperature extremes in marine areas. While land surfaces can become very hot in summer and cold in winter, the ocean's heat capacity keeps marine areas relatively cooler in summer and warmer in winter. This leads to a more balanced and moderate climate throughout the year. 4. Continental versus coastal. The differences in temperature patterns are most pronounced in continental, interior, areas compared to coastal regions. Coastal regions often experience less temperature variation due to their proximity to the ocean, which helps moderate the local climate. In summary, the higher humidity and heat capacity of water in marine areas, along with more consistent greenhouse gas concentrations, contribute to slower warming and cooling processes. This results in marine areas being generally milder and less prone to extreme temperature fluctuations compared to terrestrial areas. The seasonal differences between these two environments are most noticeable in continental interiors, where temperature extremes can be more pronounced. When the temperature distribution map of January and July is examined, it is seen that the highest winter temperatures in Turkey are experienced on the Mediterranean coast, and the highest summer temperatures are experienced in the southeastern Anatolia region. This is due to the concentration of greenhouse gases in the atmosphere. The amount of greenhouse gases in the Mediterranean coastline is higher than in the southeastern Anatolia region. You're correct that greenhouse gases, including water vapor, carbon dioxide, methane, and others, play a crucial role in regulating the Earth's temperature. They act as a natural blanket around the planet, helping to trap some of the heat radiated from the Earth's surface, which prevents excessive cooling. This greenhouse effect is essential for maintaining temperatures suitable for life on Earth. In regions with low levels of greenhouse gases or in specific conditions, such as deserts, the absence of this natural blanket can lead to significant temperature variations between day and night, as well as between seasons. Here's why. 1. Daytime heating. In desert regions, the lack of moisture and cloud cover allows the sun's energy to heat the surface intensely during the day. The ground absorbs and stores heat, causing daytime temperatures to rise significantly. 2. Radiative cooling at night. At night, without the insulating effect of greenhouse gases, the heat stored in the ground is rapidly radiated back into space. This leads to a rapid drop in temperatures, resulting in cold nights and a significant daily temperature range. 3. Seasonal variations. Deserts often experience extreme temperature differences between summer and winter. During the day, the intense sunlight causes extremely hot conditions in summer, while in winter, the lack of cloud cover allows heat to escape rapidly at night, leading to very cold temperatures. It's important to note that the Earth's climate system is complex, and temperature variations are influenced by a combination of factors, including the presence of greenhouse gases, solar radiation, regional geography, and local atmospheric conditions. Greenhouse gases contribute to overall climate patterns and can help moderate temperature extremes. Understanding these processes is vital for predicting and responding to climate changes, as well as managing the impacts of extreme temperature variations in different regions, especially those prone to desert climates. The duration of insolation, or incoming solar radiation, significantly impacts daily temperature patterns. Here's a more detailed explanation of how insolation duration affects daily temperature variations. 1. Insolation duration and daily temperature patterns. Insolation and heating. As you mentioned, the duration of insolation, or the number of daylight hours, directly affects the amount of solar energy received by a location. More daylight hours mean more time for heating, and this leads to higher daytime temperatures. This is why the highest temperatures of the day often occur a few hours after solar noon, when the Earth's surface has absorbed the most energy. Cooling at night. During the night, when the sun is no longer providing energy, the Earth's surface starts to lose heat through radiation. The absence of incoming solar radiation allows the surface to cool down. As a result, the coldest moment of the day usually occurs just before sunrise because the surface has been cooling throughout the night. 2. Other factors. While insolation duration is a critical factor, other elements can influence daily temperature patterns, including humidity, cloud cover, wind, and geographical features. For instance, cloud cover can moderate temperature extremes by reflecting sunlight or trapping heat, and humidity can affect how heat is retained or released. 3. Seasonal changes. It's important to note that insolation duration changes with the seasons. In summer, there are longer daylight hours, leading to higher daytime temperatures, while winter days are shorter and cooler. Seasonal variations in insolation duration contribute to the differences in temperatures between summer and winter. Understanding these principles helps explain daily temperature variations and why the timing of temperature extremes differs from one location to another. The interplay of insolation, radiation, and atmospheric conditions contributes to the overall climate and weather patterns experienced in a region. You've provided an accurate description of how temperature changes with elevation in the troposphere. This phenomenon is known as the environmental lapse rate, and it's an important concept in meteorology and climatology. Here's a bit more information. Environmental lapse rate, ELR. The environmental lapse rate refers to the rate at which air temperature changes with increasing altitude in the Earth's troposphere. On average, the temperature decreases by approximately 1 degree Celsius per 200 meters, or about 3.5 degrees Fahrenheit per 1,000 feet, of ascent. However, this rate can vary depending on local conditions. Reasons for the lapse rate. The primary reason for this decrease in temperature with increasing altitude is the difference in heat absorption and emission between the Earth's surface and the atmosphere. The Earth's surface is heated by incoming solar radiation during the day. This heat is then radiated back into the atmosphere, warming the air closest to the surface. As you ascend in the troposphere, there is less heat generated by the Earth's surface, and you encounter cooler air. Additionally, the air at higher altitudes is less dense and contains fewer heat-absorbing gases. These factors contribute to the decrease in temperature. Variability. While the standard environmental lapse rate is a helpful guideline, it's essential to note that the actual lapse rate can vary. In some cases, temperature inversions can occur, where the temperature increases with altitude. This is more common under specific atmospheric conditions and often leads to stable air, trapping pollutants near the surface. Significance. Understanding the environmental lapse rate is crucial for meteorologists and climatologists, as it helps predict weather conditions, temperature variations, and temperature-related phenomena. It's also essential for aviation, as it affects the performance of aircraft and influences weather patterns. In summary, the environmental lapse rate is a fundamental concept that explains the decrease in temperature with altitude in the troposphere. It's a key factor in understanding weather and climate, as well as in various applications related to atmospheric science and aviation. The term elevation is mainly used when referring to points on the Earth's surface, while altitude or geopotential height is used for points above the surface, such as an aircraft in flight or a spacecraft in orbit, and depth is used for points below the surface. The elevation of a place causes its atmosphere to become thinner. Thin atmosphere holds less heat. She is like a blanket. If she is thin, less energy absorb and radiate. The analogy comparing the atmosphere's thickness to a blanket is a helpful way to understand the role of elevation in shaping the climate and temperature of a location. Here's a bit more detail on this concept. Elevation and the atmosphere. As you ascend in altitude, the atmosphere becomes less dense because there is less air above you. This thinning of the atmosphere has several important effects on temperature and climate. The atmosphere acts like a blanket, as you mentioned. It contains gases that can absorb and trap heat from the Earth's surface. This process is known as the greenhouse effect and is essential for maintaining a habitable climate on Earth. At higher elevations, the atmosphere is thinner, which means it contains fewer greenhouse gases and has a reduced capacity to absorb and trap heat. As a result, the temperature tends to be lower at higher elevations. Temperature and elevation. The lapse rate I mentioned earlier describes how temperature decreases with increasing altitude. This phenomenon occurs because there are fewer air molecules at higher elevations to retain heat. In many mountainous regions, such as the Himalayas or the Rocky Mountains, you'll find that as you ascend, the temperature typically decreases. This is why high mountain peaks are often covered in snow and experience colder conditions, even in warmer seasons. Elevation not only influences temperature but also affects other aspects of climate, including precipitation patterns. Mountains can block the movement of moist air masses, leading to variations in rainfall and the formation of rain shadows. Applications. The relationship between elevation and temperature is crucial for various fields, such as agriculture, tourism, and weather forecasting. Farmers need to know how temperature changes with altitude to make decisions about crops, and tourists often choose destinations based on the climate they prefer. Scientists and meteorologists use this knowledge to understand climate zones, make weather predictions, and study the effects of climate change. In summary, your description of the atmosphere's thinning with elevation and its role in temperature change is accurate. The concept is a fundamental part of understanding climate and weather, and it has practical implications in various aspects of our lives. Land and water have different thermal properties, which cause them to warm up and cool down at different rates. Here's why this happens. Land heats and cools quickly. Land has a lower heat capacity compared to water. Heat capacity is the amount of heat energy required to raise the temperature of a substance. Land heats up and cools down relatively quickly because it has a lower heat capacity. This is why you can often feel the ground warming up on a sunny day and cooling down at night. Water heats and cools slowly. Water has a high heat capacity. It can absorb and store a large amount of heat energy without changing temperature significantly. This property causes water to heat up and cool down more slowly compared to land. Large bodies of water, like oceans and lakes, can act as heat reservoirs. They absorb heat during the day and release it slowly at night. This moderates the temperature variations near bodies of water, resulting in milder and more stable climates. Implications. The difference in the rate of heating and cooling between land and water has several consequences for climate and weather. Coastal areas often experience milder and more moderate temperatures due to the temperature moderating effect of the nearby ocean. Inland regions, especially deserts, can have extreme temperature variations, with scorching hot days and cold nights. Bodies of water, such as lakes or large rivers, can influence the climate of surrounding areas, making them more habitable. Microclimates. These differences in heating and cooling rates also create microclimates, which are localized climate variations within a broader region. For example, urban areas with asphalt and concrete may heat up more quickly and become warmer than nearby rural areas. In summary, the distinct thermal properties of land and water lead to variations in how they respond to solar radiation and other heat sources, affecting local and regional climates and giving rise to microclimates. This interplay is a fundamental aspect of Earth's climate system. The distribution of land and water across the Northern Hemisphere and the Southern Hemisphere plays a significant role in shaping the climate differences between these two regions. Here's why this happens. 1. Land-water distribution. The Northern Hemisphere has a greater land-to-water ratio compared to the Southern Hemisphere. This means there is more landmass in the Northern Hemisphere and more ocean in the Southern Hemisphere. 2. Heat capacity. As mentioned earlier, land heats up and cools down more quickly than water due to differences in heat capacity. Land has a lower heat capacity, so it responds rapidly to changes in solar radiation and air temperature. 3. Specific heat. Water has a higher specific heat compared to land. Specific heat is the amount of heat energy required to raise the temperature of a given mass of a substance. Water's high specific heat allows it to absorb and store a significant amount of heat energy without experiencing large temperature changes. 4. Moderation by oceans. Oceans act as heat reservoirs, absorbing and releasing heat slowly. They moderate the temperatures of coastal areas and nearby landmasses, resulting in milder and more stable climates. 5. Landmass extremes. Landmasses in the Northern Hemisphere, especially in regions far from the moderating influence of the ocean, can experience more extreme temperature variations. This leads to the presence of both very cold winters and hot summers in continental interiors. 6. Seasonal differences. The seasonal differences in temperature in the Northern Hemisphere are often more pronounced compared to the Southern Hemisphere due to the larger landmass area. This results in distinct seasons with cold winters and warm summers. In summary, the distribution of land and water in the Northern Hemisphere leads to more rapid temperature changes and a wider range of seasonal temperatures compared to the Southern Hemisphere. Oceans in the Southern Hemisphere, with their moderating influence, contribute to milder and more consistent climates in many regions. These geographical factors are key drivers of climate differences between the hemispheres. Lands and bodies of water exhibit distinct differences in how they respond to solar radiation and temperature changes, leading to variations in daily and seasonal temperature patterns. Lands warm up quickly when exposed to sunlight during the day, resulting in higher daytime temperatures, especially in summer. Cool down rapidly at night when there is no sunlight, leading to lower nighttime temperatures. In winter, they also experience larger temperature fluctuations, with colder conditions due to reduced solar heating. Water, seas and oceans warm up more slowly when exposed to sunlight, causing them to have a moderating effect on nearby coastal areas. As a result, coastal areas experience less extreme temperature variations compared to inland regions. Water has a higher specific heat capacity, which means it can store heat more effectively. This results in a lag in temperature changes. Coastal areas tend to be cooler during the day and warmer at night, with milder temperatures. Water bodies help maintain more stable temperatures throughout the year, with less variation between seasons. Winters are milder, and summers are cooler in coastal areas near large bodies of water. These differences in how land and water respond to solar radiation and temperature changes are key factors influencing local and regional climates. Coastal areas benefit from the moderating influence of the ocean, resulting in more comfortable and consistent temperatures, while continental interiors often experience greater temperature extremes. Humidity plays a significant role in moderating temperature extremes and reducing temperature differences in a given area. Here's how humidity affects temperature. 1. Cooling effect. When air is dry, low humidity, it has the capacity to absorb more heat. In contrast, when air is humid, high humidity, it's less efficient at absorbing heat. This is why humid conditions can feel warmer, because the body's ability to cool through perspiration is reduced. 2. Warming effect. Conversely, in a dry environment, temperature swings between day and night can be more pronounced. Humidity helps to slow down the cooling process at night, preventing temperatures from dropping as drastically. 3. Maritime influence. Areas close to large bodies of water, such as oceans, seas, or lakes, often experience milder and more stable temperatures because the water helps moderate temperature extremes. Water has a high heat capacity, meaning it can store and release heat slowly, which keeps nearby areas from getting too hot or too cold. 4. Humidity and climate. The presence of humidity, or lack thereof, can also influence the climate of a region. Humid climates are often characterized by milder, more stable temperatures and tend to be found in coastal and tropical areas. Arid or desert climates, on the other hand, are known for their extreme temperature variations due to low humidity levels. In summary, humidity has a significant impact on local and regional climates, helping to keep temperatures more moderate and reducing the severity of both hot and cold extremes. The area around the equator, also known as the tropics, receives nearly vertical insolation throughout the year, meaning the sun's rays strike the Earth's surface almost directly. While it is generally very warm and hot in the tropics, it's not necessarily the hottest places on Earth for several reasons. 1. Elevation. Elevation or altitude plays a significant role in determining local temperatures. In many tropical regions, there are high mountain ranges, like the Andes, the Himalayas, or the Rockies. As you ascend these mountains, temperatures drop. For example, cities in the mountains of the tropics can be much cooler than lowland areas. 2. Ocean currents. Ocean currents influence the temperature of coastal areas. For example, areas near cold ocean currents can have cooler temperatures, even if they're in the tropics. Conversely, areas near warm ocean currents can experience warmer temperatures. 3. Vegetation and land cover. Forested or vegetated areas can be cooler due to the shading and cooling effects of plants. In contrast, urban areas with little vegetation and a lot of concrete and asphalt can be significantly warmer due to the urban heat island effect. 4. Local geography. The local geography, such as valleys and canyons, can influence temperatures. Valleys tend to accumulate cold air, while canyons may trap heat, affecting local temperatures. 5. Seasonal variations. Many tropical regions experience wet and dry seasons. During the wet season, temperatures can be somewhat moderated by cloud cover and rain, while in the dry season, they can be quite hot. 6. Latitude. While the equator is hot, areas closer to the tropics of Cancer and Capricorn can also experience very high temperatures. For instance, deserts like the Sahara in Africa and the Arabian Desert in the Middle East are extremely hot because they are closer to the Tropic of Cancer and receive intense sunlight. In summary, the hottest places on Earth can vary due to a combination of factors, including elevation, local geography, vegetation, ocean currents, and distance from the equator. While the tropics are generally hot, local conditions and other factors can lead to even higher temperatures in specific regions. Air masses play a crucial role in shaping the weather and climate of different regions, including Turkey. The air masses you mentioned, those of Iceland, Siberia, Azores, Basra, and North Africa origin, have distinct characteristics and can have a significant impact on the weather in Turkey. 1. Icelandic air mass. This air mass originates in the North Atlantic Ocean, near Iceland. It is typically cold and moist. When it moves towards Turkey, it can bring cold temperatures and precipitation, especially in the northern and western parts of the country. In winter, this air mass can result in cold spells and snowfall. 2. Siberian air mass. Originating in Siberia, Russia, this air mass is known for its extreme cold. When it reaches Turkey, especially the eastern and northeastern regions, it can bring frigid temperatures. This air mass is associated with very cold and dry conditions in winter. 3. Azores air mass. The Azores High, located in the North Atlantic Ocean near the Azores Islands, generates this air mass. It is warm and humid. When it influences Turkey, it can bring mild and relatively humid conditions. This air mass often contributes to warm and pleasant weather in the summer. 4. Basra air mass. This air mass originates in the Persian Gulf region, near Basra, Iraq. It tends to be hot and dry. When it moves northward into Turkey, especially in the southeastern and southern regions, it can result in hot and dry conditions. This air mass is often associated with high temperatures and low humidity. 5. North African air mass. Originating in North Africa, this air mass is typically hot and dry. When it reaches southern and southwestern parts of Turkey, it can contribute to hot and arid conditions. It is common in the summer and can lead to heat waves. These air masses interact and compete with each other, influencing the weather patterns and climate of Turkey. The diverse geography of the country, with its coastal areas, mountains, and plains, further enhances the complexity of the weather, making Turkey a region with varied and sometimes unpredictable climate patterns. Condensation is the process by which a gas or vapor transforms into a liquid state. This transformation occurs when the temperature of the gas is lowered, or when the gas comes into contact with a surface or substance that is colder than the gas. As the gas loses thermal energy, its particles slow down, move closer together, and form liquid droplets. Condensation is a fundamental natural process that has various effects and applications in our daily lives. Here are some key points about condensation and its products. 1. Formation of clouds. Condensation plays a critical role in the formation of clouds. When warm, moist air rises and cools at higher altitudes, water vapor in the air condenses to form tiny water droplets or ice crystals. These droplets or crystals come together to create visible clouds in the sky. 2. Dew formation. Condensation can lead to the formation of dew on surfaces like grass, leaves, and car windshields during the night. As the ground cools after sunset, it can cause the surrounding air to reach its dew point temperature, leading to the condensation of water vapor on surfaces. 3. Fog. Fog is essentially a cloud that forms near the ground. It is created when moist air near the surface cools and reaches its dew point temperature, causing water vapor to condense into tiny water droplets that reduce visibility. 4. Rain. Raindrops are formed through the coalescence of water droplets in clouds. As smaller water droplets combine with others due to condensation and collide, they grow in size until they are heavy enough to fall to the ground as rain. 5. Distillation. Condensation is a key component of distillation processes used in various industries and laboratories. By heating a mixture of liquids and then cooling the vapor, different components can be separated and collected as condensates. 6. Heat exchange. Condensation is used in heat exchangers to transfer heat. For example, in air conditioning systems, warm air is cooled, and its water vapor condenses, releasing latent heat and helping to reduce the temperature in a room. 7. Applications in chemical and pharmaceutical industries. Condensation is widely used in the chemical and pharmaceutical industries for various processes, including the synthesis of chemicals and the purification of products. 8. Energy generation. In power plants, steam turbines operate on the principle of steam condensing into water to generate energy. The steam is condensed in a cooling system to release heat and turn the turbines. 9. Food and beverage processing. Condensation is used in the production of various food and beverage products, such as distilled spirits, where alcohol vapor is condensed and collected as the final product. Condensation is a natural phenomenon with numerous practical applications across various fields, contributing to the formation of weather patterns, the separation of substances, and the operation of many industrial processes. Exactly, when the air reaches its saturation point, which is the point at which it can no longer hold all the water vapor, excess water vapor begins to condense into visible water droplets or ice crystals. This is a fundamental principle behind cloud and fog formation. Here's how it works. 1. Saturation point. The air can hold a certain amount of water vapor depending on its temperature and pressure. When the air contains water vapor near its capacity to hold it, relative humidity is close to 100%, it's said to be near its saturation point. 2. Cooling or adding moisture. There are several ways in which the air can reach its saturation point. Cooling. If the air cools, its capacity to hold water vapor decreases. When the temperature drops to the dew point, the temperature at which the air becomes saturated, condensation occurs. This cooling can happen when warm, moist air rises and cools at higher altitudes, leading to cloud formation. Adding moisture. If more moisture is introduced into the air, pushing it beyond its capacity to hold water vapor, excess moisture condenses into visible water droplets. 3. Visible condensation. When the excess water vapor condenses into tiny water droplets or ice crystals, it becomes visible as clouds or fog. These are essentially collections of countless tiny water droplets suspended in the air. Clouds and fog are excellent visual indicators of atmospheric conditions. They provide insights into temperature, humidity, and air movements. Different types of clouds can tell meteorologists and scientists about the current and future weather patterns. Additionally, fog can significantly affect visibility and is of particular concern to transportation and safety. Understanding the process of condensation and cloud formation is key to meteorology, climate science, and environmental studies. It's an important part of how the Earth's atmosphere functions and influences our weather and climate. Clouds are visible collections of water droplets or ice crystals suspended in the Earth's atmosphere. They form when moist air rises, cools, and reaches its saturation point, causing water vapor to condense into tiny droplets around microscopic particles called cloud condensation nuclei. Clouds are crucial components of the Earth's climate and weather systems, and they come in various shapes and sizes. Meteorologists classify clouds into several basic cloud types based on their appearance and altitude in the atmosphere. Here are some common cloud types. 1. Cirrus clouds, C. These high-altitude clouds appear wispy and thin. They typically form above 20,000 feet, 6,000 meters, and consist of ice crystals. Cirrus clouds are often indicators of fair weather but can also signal approaching storms. 2. Cumulus clouds, CHU. Cumulus clouds are puffy, white clouds with a flat base. They develop in the lower to middle levels of the atmosphere and are often associated with fair weather. When they grow taller and larger, they can develop into cumulonimbus clouds, which bring thunderstorms. 3. Stratus clouds, ST. Stratus clouds form in low layers and appear as uniform, grayish sheets covering the sky. They often indicate overcast or drizzly weather. 4. Nimbostratus clouds, NS. Nimbostratus clouds are thick and dark stratus clouds that bring steady precipitation. They can obscure the sky and linger for long periods. 5. Cirrostratus clouds, Cs. Cirrostratus clouds are high, thin clouds that create a milky or hazy veil across the sky. They can signal the approach of a warm front. 6. Altocumulus clouds, AC. Altocumulus clouds are mid-level clouds with a patchy, puffy appearance. They often appear in small groups or layers and are associated with fair weather. 7. Stratocumulus clouds, SC. Stratocumulus clouds are low-lying clouds that appear as a mixture of gray and white patches or rolls. They often cover the entire sky and can bring drizzle or light rain. 8. Cumulonimbus clouds, CB. These are towering, anvil-shaped clouds that can reach high into the atmosphere. Cumulonimbus clouds bring thunderstorms, heavy rain, and sometimes severe weather. 9. Cirrocumulus clouds, CC. Cirrocumulus clouds are small, high-altitude clouds that appear in clusters. They are associated with fair weather. 10. Lenticular clouds. Lenticular clouds have a lens or saucer-shaped appearance and often form near mountains or hilly terrain when moist air flows over obstacles. They are commonly mistaken for UFOs due to their unusual shape. Clouds play a crucial role in Earth's climate system by reflecting sunlight back into space, trapping heat, and influencing weather patterns. Meteorologists use cloud observations to make short-term weather forecasts and study long-term climate trends. Understanding cloud types and their characteristics is essential for weather and climate research. Clouds are visible collections of water droplets or ice crystals suspended in the Earth's atmosphere. They form when moist air rises, cools, and reaches its saturation point, causing water vapor to condense into tiny droplets around microscopic particles called cloud condensation nuclei. Clouds are divided into three groups according to their height. Low clouds are cloud types that typically form at lower altitudes in the Earth's atmosphere, generally below 2,000 meters. They include stratus and cumulus clouds. These low cloud formations have distinct characteristics and play significant roles in weather patterns. 1. Stratus clouds, ST. Stratus clouds are low-lying cloud layers with a uniform, flat appearance. They often cover the entire sky, creating an overcast, gray or white ceiling. Stratus clouds are associated with stable atmospheric conditions and can bring light precipitation, such as drizzle or light rain. When stratus clouds form near the ground, they are referred to as fog. 2. Cumulus clouds, CHU. Cumulus clouds are usually puffy, white clouds with a flat, well-defined base. They tend to form in the lower to middle layers of the atmosphere. Cumulus clouds are typically associated with fair weather, but when they grow vertically, they can develop into cumulonimbus clouds, which are associated with thunderstorms. These low clouds contribute to various weather conditions, including overcast skies, fog, and scattered light precipitation. Meteorologists use observations of low cloud types to assess current weather conditions and predict short-term weather changes, making them an important element of weather forecasting and climate study. Middle clouds, as the name suggests, are cloud formations that occupy the middle layers of the Earth's atmosphere, generally between 2,000 to 6,000 meters in altitude. They are an important element in understanding weather patterns and meteorology. Two common types of middle clouds are altostratus and altocumulus. 1. Altostratus clouds. Altostratus clouds are gray or blue-gray, uniform cloud layers that often cover the entire sky. They are typically thicker than high cirrostratus clouds but thinner than low stratus clouds. Altostratus clouds often indicate overcast skies and can be seen ahead of a warm front or a developing storm system. These clouds may bring continuous, steady precipitation, such as rain or snow. 2. Altocumulus clouds, AC. Altocumulus clouds are mid-level clouds that appear as white or gray puffy clouds, often occurring in patches or groups. They are composed of water droplets and are associated with fair to partly cloudy weather. Altocumulus clouds are sometimes seen before or after a storm and are not typically precipitation producers. In some cases, they can indicate atmospheric instability and the potential for thunderstorms. Middle clouds, including altostratus and altocumulus, have various appearances and roles in meteorology. Meteorologists closely monitor these cloud types to assess current weather conditions and provide valuable information for weather forecasts and climate analysis. High clouds are cloud formations that occur at high altitudes, typically above 20,000 feet, 6,000 meters. They are composed primarily of ice crystals and serve as important indicators of upper-level atmospheric conditions. Two common types of high clouds are cirrocumulus and cirrostratus. 1. Cirrocumulus clouds, CC. Cirrocumulus clouds are small, white, and puffy cloudlets that form in high-altitude layers. They often appear in delicate ripples or rows, creating a mackerel sky pattern. These clouds are composed of tiny ice crystals and water droplets. Cirrocumulus clouds are associated with fair weather and often indicate a stable atmosphere. They might form during the approach of a warm front or an upper-level disturbance. 2. Cirrostratus clouds, Cs. Cirrostratus clouds are thin, wispy cloud layers that can cover the entire sky. They often create a milky or hazy appearance, partially obscuring the sun or moon. These high clouds are composed of ice crystals and are often seen before a warm front or occluded front approaches. Cirrostratus clouds may produce a halo around the sun or moon due to the bending of light by the ice crystals. High clouds play a significant role in forecasting weather conditions, as their presence or changes in their appearance can provide valuable information about upper-level disturbances and the approach of weather systems. Meteorologists use these cloud types to monitor atmospheric conditions and make predictions about weather patterns, especially for those systems occurring in the upper levels of the atmosphere. Fog is a meteorological phenomenon that occurs near the surface of the Earth when there is a high concentration of moisture in the air, leading to reduced visibility. It is essentially a cloud that forms at ground level. Fog can vary in thickness and can occur in various locations and under different weather conditions. Here are some key points about fog. 1. Formation. Fog typically forms when warm, moist air comes into contact with a cooler surface, causing the air to cool rapidly and reach its dew point, which is the temperature at which air becomes saturated with moisture. When the air cools to this point, the excess water vapor in the air condenses into tiny water droplets or ice crystals, forming fog. 2. Types of fog. Radiation fog, also known as ground fog. Radiation fog forms on clear, calm nights when the ground loses heat through radiation. The air near the ground cools, and if it reaches its dew point, radiation fog can form. This type of fog is common in valleys and low-lying areas. Advection fog. Advection fog occurs when warm, moist air moves over a cooler surface, causing the air to cool and reach its dew point. It's often associated with coastal areas where warm, moist air from the sea moves over cooler land surfaces. Upslope fog. This type of fog forms when moist air is forced to rise along the slopes of hills or mountains. As the air ascends, it cools, and fog can develop. Evaporation, steam, fog. Steam fog arises when cold, dry air moves over warmer water. The heat from the water evaporates into the air, creating fog. Frontal fog. Frontal fog can develop when warm and cold air masses meet, and the warm, moist air is lifted over the cold air. 3. Impact. Fog can significantly reduce visibility, making travel hazardous. It can lead to traffic accidents and disruptions in air travel. Fog can also affect maritime operations, including shipping and fishing. 4. Dissipation. Fog generally dissipates when the air temperature rises, causing the fog to evaporate. It can also be dispersed by wind or mixed out when the air becomes more turbulent. 5. Fog forecasting. Meteorologists use various tools and data to forecast the formation and dissipation of fog. Visibility forecasts and local observations play a crucial role in predicting fog events. Fog is an important aspect of weather forecasting, and its presence or absence can have a significant impact on daily activities, transportation, and safety, especially in regions prone to foggy conditions. Fog is essentially a type of cloud that forms near the surface of the Earth. It occurs when the air near the ground becomes saturated with moisture and water vapor condenses into tiny water droplets or ice crystals. Fog can significantly reduce visibility and can be especially common in areas where moist, relatively warm air comes into contact with cooler surfaces, such as the ground or bodies of water. Fog is essentially a cloud at ground level and can have different types and characteristics, as mentioned earlier. Radiation fog, also known as ground fog, is a type of fog that forms overnight and is most common during the cooler months of the year. It typically occurs when the ground loses heat through radiation, which causes the air near the surface to cool. When the temperature of the air near the ground drops to its dew point, the temperature at which air becomes saturated and moisture condenses into water droplets, radiation fog forms. This type of fog is usually associated with clear, calm nights when the ground can lose heat rapidly. As the air cools and reaches its dew point, moisture in the air condenses to form tiny water droplets, creating a thick fog that can reduce visibility significantly. Radiation fog often dissipates once the sun rises and begins to warm the surface, causing the fog to lift. It's a common phenomenon in areas with clear skies, light winds, and relatively high humidity, and it's often seen in low-lying areas, river valleys, or coastal regions. Advection fog is a type of fog that forms when warm, moist air moves horizontally over a colder surface, causing the air to cool to its dew point temperature and condense into water droplets. Unlike radiation fog, which forms from cooling of the ground, advection fog is a result of the horizontal movement of air masses. Here's how advection fog typically forms. 1. Warm, moist air moves over a colder surface. When warm, moist air moves over a cooler land or water surface, it begins to cool down. If the cooling causes the air to reach its dew point, condensation occurs. 2. Condensation into fog. As the warm, moist air continues to cool, it reaches the dew point temperature, and moisture in the air condenses into tiny water droplets. This condensation results in the formation of a thick fog layer. Advection fog can occur in various geographic settings, such as coastal areas where warm, moist air from the ocean flows over a colder coastal landmass. It can also develop over agricultural areas or regions with temperature differences between land and water. Unlike radiation fog, advection fog doesn't require clear skies and calm conditions to form, making it more common in areas with constant air movement. This type of fog can persist for longer periods than radiation fog and often requires specific weather patterns to dissipate, such as changes in wind direction or temperature. Steam fog, also known as evaporation fog or sea smoke, is a type of fog that forms when cold, dry air passes over relatively warmer water. This phenomenon typically occurs in colder climates, especially during the transition from winter to spring or from fall to winter. Steam fog can often be observed over bodies of water, such as lakes, rivers, and even the ocean. Here's how steam fog typically forms. 1. Cold, dry air. A mass of cold, dry air moves over a body of water that is relatively warmer. The temperature difference between the cold air and the warmer water is essential for the formation of steam fog. 2. Evaporation. When the cold, dry air comes into contact with the warmer water, it causes the water's surface to evaporate. This evaporation releases water vapor into the air. 3. Condensation. As the water vapor rises into the cold air, it quickly cools and reaches its dew point temperature. Condensation occurs, forming tiny water droplets in the air. 4. Fog formation. The condensation results in the formation of a fog layer just above the water's surface. This fog appears as a steaming or smoking effect, hence the name steam fog. Steam fog is a relatively localized phenomenon and usually occurs in the early morning when the temperature difference between the air and water is at its maximum. As the day progresses and temperatures rise, the steam fog typically dissipates. This type of fog can create visually striking scenes, especially when it hovers over lakes or rivers, and it is often associated with colder seasons and cool bodies of water. Orographic fog, also known as upslope fog, forms when moist air is lifted as it moves up the windward side of a mountain or hill. As the air ascends, it cools, and if it reaches its dew point temperature, condensation occurs, leading to the formation of fog. Orographic fog is a common meteorological phenomenon in mountainous regions, and it is closely related to the orographic effect, which influences weather patterns and precipitation. Here's how orographic fog typically forms. 1. Moist air. Orographic fog requires a source of moist air. This air may come from bodies of water, such as oceans or lakes, and it must be laden with moisture in the form of water vapor. 2. Mountain barrier. Orographic fog forms when this moist air encounters a mountain or hill. The moist air is forced to ascend due to the topography of the land. As it rises, it undergoes adiabatic cooling, which means it cools as it ascends without any exchange of heat with the surrounding environment. 3. Dew point. As the moist air rises, it reaches higher altitudes with lower temperatures. If it cools to the point where its temperature equals the dew point temperature, the temperature at which air becomes saturated with moisture, condensation occurs, forming tiny water droplets that make up the fog. 4. Fog formation. Orographic fog is typically observed on the windward side of the mountain or hill, where the air is forced to rise. The fog can extend over the mountain slopes and into valleys on the windward side. On the leeward side, the side facing away from the oncoming moisture-laden air, the air descends, warms, and the fog dissipates. Orographic fog can be persistent and affect visibility in mountainous regions, impacting transportation and local climates. It often occurs in regions with prevailing moist winds that encounter topographic barriers, such as coastal mountains or large hills. Precipitation fog, also known as frontal fog, is a type of fog that forms in conjunction with precipitation. It occurs when rain, drizzle, or snow falls through a layer of relatively dry air near the surface. As the precipitation descends, it saturates the surrounding air, causing fog to develop. Precipitation fog can be observed in various weather conditions and is often associated with specific weather fronts. Here's how precipitation fog typically forms. 1. Precipitation. Precipitation, such as rain, drizzle, or snow, falls from the cloud layer above. 2. Dry air near the surface. There is a layer of relatively dry air near the ground. This dry air may result from a previous high-pressure system, local subsidence, or other atmospheric conditions. 3. Interaction with dry air. As the precipitation descends through the dry air layer, it begins to evaporate and cool the surrounding air. This cooling effect lowers the air temperature, causing the air to reach its dew point temperature. 4. Saturation. When the descending air reaches its dew point temperature, it becomes saturated with moisture. At this point, the air cannot hold additional moisture, and condensation occurs, forming tiny water droplets. This process is similar to how dew forms on surfaces when the air temperature drops to the dew point. 5. Fog formation. The tiny water droplets created by condensation make up the fog. Precipitation fog often has a misty or drizzly appearance and is closely associated with the falling precipitation. Visibility may be significantly reduced when precipitation fog occurs, leading to hazardous driving conditions and the need for caution. Precipitation fog is common in areas where rain, drizzle, or snow interacts with dry, cool air near the surface. It can be observed along the leading edge of warm fronts, cold fronts, and occluded fronts, as well as during light rain or drizzle events in various weather conditions. The intensity and duration of precipitation fog depend on factors such as the rate of precipitation, air temperature, and humidity levels near the surface. Freezing fog is a meteorological phenomenon characterized by the presence of fog when surface temperatures are at or below freezing, 0 degrees Celsius or 32 degrees Fahrenheit. This type of fog is composed of tiny water droplets that remain in a liquid state despite the sub-freezing temperatures. Freezing fog can create a variety of hazards and challenges, particularly on roadways and other exposed surfaces. Here's how freezing fog forms and some of its key characteristics. 1. Fog formation. Fog is essentially a cloud that forms at or near the Earth's surface when the air is saturated with moisture and the temperature is near or below freezing. 2. Supercooled water droplets. In freezing fog, the fog consists of supercooled water droplets, which means these droplets remain in a liquid state despite temperatures being below freezing. This occurs when there are no particles or nuclei around which the water droplets can freeze. 3. Ice accretion. When freezing fog droplets come into contact with cold surfaces, they freeze on contact, creating a thin layer of ice. This ice accretion can form on roads, trees, power lines, and other objects. 4. Reduced visibility. Like other types of fog, freezing fog significantly reduces visibility, making it challenging for drivers and pedestrians. The presence of ice on roadways and walkways can create slippery and hazardous conditions. 5. Hoarfrost. Freezing fog can also lead to the formation of hoarfrost on surfaces. Hoarfrost is a white, crystalline deposit of ice that forms when water vapor in the air undergoes deposition directly to ice crystals. Freezing fog is more likely to occur in areas with the right meteorological conditions, including high humidity and cold temperatures near or below freezing. It is often associated with stable atmospheric conditions that trap moisture near the surface, preventing it from rising and dissipating. Freezing fog is most common during the winter months and can create treacherous conditions, especially on roadways. Drivers need to exercise caution when traveling through areas affected by freezing fog to avoid accidents and slipping on icy surfaces. Frontal fog, also known as frontal boundary fog, is a type of fog that forms in association with the passage of a weather front. Weather fronts are boundaries between different air masses, and when warm, moist air encounters cooler air, the conditions can be favorable for the development of frontal fog. Here's how frontal fog forms and its key characteristics. Formation. 1. Weather front. Frontal fog occurs along or near the leading edge of a weather front. Weather fronts are classified into warm fronts and cold fronts. When a warm front advances and replaces a mass of cooler air, warm, moist air rises over the cooler air, and condensation occurs, leading to the formation of fog. 2. Saturation. As the warm, moist air is forced to rise over the colder air, it cools and reaches its dew point, causing the water vapor in the air to condense into tiny water droplets. This condensation is what creates the fog. 3. Advancement. Frontal fog typically forms ahead of the front's boundary and may extend over a large area as the front moves. Key characteristics. 1. Visibility reduction. Frontal fog significantly reduces visibility, often to a level where it can become hazardous for drivers, pilots, and other outdoor activities. The fog can be quite dense and persistent. 2. Moisture source. Frontal fog derives its moisture from the warmer, moist air mass rising and condensing as it encounters the cooler air. 3. Temperature differential. The contrast in temperatures between the advancing warm air and the pre-existing cold air is a critical factor in frontal fog formation. The greater the difference in temperature, the more likely it is for frontal fog to develop. 4. Frontal passage. The fog's onset is often closely tied to the passage of the front. As the front moves, the fog may dissipate or shift locations accordingly. 5. Variable duration. Frontal fog can persist for varying lengths of time, depending on factors such as the speed of the front and local atmospheric conditions. Frontal fog is an important weather phenomenon to be aware of, especially when traveling, as it can create challenging conditions on roads and at airports. Meteorologists monitor the movement and characteristics of weather fronts to provide forecasts and warnings related to the formation of frontal fog. Dew is a type of atmospheric moisture that forms as a result of the condensation of water vapor in the air. It typically occurs when the temperature of surfaces, such as grass, leaves, or other objects, falls below the dew point temperature of the surrounding air. Dew forms during the late evening or early morning hours, and it appears as small water droplets that accumulate on surfaces, giving them a wet or moist appearance. Here are the key factors and conditions related to the formation of dew. 1. Temperature difference. Dew forms when the temperature of a surface becomes cooler than the dew point temperature of the surrounding air. The dew point temperature is the temperature at which air becomes saturated with moisture and cannot hold all the water vapor it contains. 2. Clear and calm nights. Dew formation is most common on clear and calm nights when there is little to no wind. Under these conditions, the ground and other surfaces radiate heat into the cold night sky, causing them to cool down. 3. Radiational cooling. The cooling of the Earth's surface occurs through a process called radiational cooling. As the ground loses heat through radiation, it cools the air in direct contact with it. 4. Saturation. When the temperature of the surface falls below the dew point temperature of the adjacent air, the air becomes saturated with moisture. The excess water vapor in the air condenses into tiny water droplets on the surface, forming dew. 5. Formation time. Dew typically forms in the early morning hours just before or around sunrise when temperatures are at their lowest. 6. Surface types. Some surfaces are more likely to accumulate dew than others. Grassy areas, leaves, car windshields, and metal objects are common places where dew forms. 7. Local conditions. Local factors, such as humidity levels, cloud cover, and the presence of vegetation, can influence the formation and intensity of dew. Dew can be an important source of moisture for plants and can contribute to local microclimates. It's also commonly observed on mornings with clear skies and calm conditions. While dew is not the same as frost, it can sometimes occur alongside frost, especially when temperatures drop to freezing or below, causing the dew to freeze and become frost. Hoarfrost, often simply referred to as frost, is a type of ice that forms when water vapor directly transitions into ice crystals on surfaces, such as grass, leaves, trees, and other objects, when the air temperature falls below freezing, 0 degrees Celsius or 32 degrees Fahrenheit. Hoarfrost is a type of frost that has a distinctive appearance, consisting of delicate, feathery ice crystals. Key characteristics and conditions associated with hoarfrost include 1. Formation process. Hoarfrost forms when the air is sufficiently cold and contains enough moisture, high humidity, to allow water vapor to undergo deposition directly from the gas phase to solid ice. This is in contrast to dew, which forms when water vapor condenses into liquid water on surfaces. 2. Clear, calm nights. Hoarfrost typically forms on clear and calm nights when the temperature drops below freezing. These conditions facilitate radiational cooling, allowing surfaces to cool rapidly. 3. Surface types. Hoarfrost tends to form on various surfaces, particularly vegetation like grass, leaves, and tree branches. The intricate ice crystals accumulate on the surfaces, giving them a frosty, white appearance. 4. Appearance. Hoarfrost crystals have a feathery or spiky appearance, with intricate, branching patterns. They can create a picturesque winter landscape, coating plants and objects with a layer of fine ice crystals. 5. Microclimates. Hoarfrost can be more prevalent in certain microclimates, such as valleys or areas with low-lying cold air that settles overnight. 6. Protective blanket. While hoarfrost can create a beautiful wintry scene, it can also have an insulating effect on plants and surfaces, protecting them from extreme cold and frost damage. 7. Difference from frost. While the term frost is sometimes used interchangeably with hoarfrost, frost can also refer to other forms of ice, including rime frost and ground frost, which may have different characteristics. Hoarfrost is a fascinating natural phenomenon that adds a touch of beauty to winter landscapes. It is often associated with cold and clear winter nights when temperatures are low and humidity is relatively high. Precipitation refers to any form of water, liquid or solid, that falls from the Earth's atmosphere to the surface. It is a vital component of the Earth's hydrological cycle, which includes the processes of evaporation, condensation, and precipitation. Precipitation can take various forms, and it plays a critical role in shaping climate, weather, and ecosystems. Here are the common types of precipitation. 1. Rain. Rain is liquid water droplets that fall from the sky when atmospheric conditions are above freezing. It is the most common form of precipitation and is essential for sustaining plant and animal life. 2. Snow. Snow consists of ice crystals that form in the atmosphere and fall as soft, white flakes. Snowfall is common in cold regions and at higher elevations. Accumulated snow can create snowpack, which serves as a water resource when it melts. 3. Sleet. Sleet is a mix of frozen raindrops and ice pellets. It occurs when raindrops freeze before reaching the ground. Sleet can create slippery conditions on surfaces. 4. Hail. Hail is composed of ice pellets that are larger and harder than sleet. Hail forms within strong thunderstorms when updrafts carry raindrops into extremely cold regions of the cloud, causing them to freeze and grow larger. 5. Freezing rain. Freezing rain occurs when rain falls while surface temperatures are below freezing. The raindrops freeze upon contact with cold surfaces, creating a layer of ice, often referred to as an ice storm. Freezing rain can be hazardous. 6. Drizzle. Drizzle consists of tiny, fine water droplets that fall from low-lying clouds. It is often associated with overcast or foggy conditions. 7. Showers. Showers are brief periods of rain or precipitation, usually associated with localized weather systems like thunderstorms. They can vary in intensity and duration. The type of precipitation that falls depends on several factors, including temperature, humidity, and the atmospheric conditions. Understanding the type of precipitation is essential for predicting weather and its impact on various activities and ecosystems. Precipitation is a key factor in providing the Earth with fresh water, replenishing rivers, lakes, and groundwater, and influencing regional and global climate patterns. Rain is formed through a process called the rain cycle or hydrological cycle, which involves several stages. Here's an overview of how rain is formed. 1. Evaporation. It all starts when the sun's energy heats up water on the Earth's surface, causing it to evaporate. This process transforms liquid water into water vapor, which is an invisible gas. 2. Condensation. The water vapor rises into the atmosphere and cools as it ascends to higher altitudes. Cooler temperatures cause the water vapor to condense into tiny water droplets. These droplets combine and form clouds. 3. Cloud formation. The condensed water droplets accumulate to form clouds. Clouds are composed of countless tiny water droplets or ice crystals suspended in the air. Clouds can take various forms, including cumulus, stratus, and cirrus, depending on their altitude and characteristics. 4. Precipitation. When the cloud droplets or ice crystals become heavy enough, they begin to fall from the cloud toward the Earth's surface. The type of precipitation, rain, snow, sleet, or hail, depends on temperature conditions. If temperatures are above freezing, rain forms. 5. Rainfall. Raindrops fall to the ground due to the force of gravity. The size of the raindrops can vary, ranging from small drizzles to larger raindrops. Rainfall provides the Earth with much needed moisture, which is essential for plant growth, replenishing water bodies, and maintaining ecosystems. 6. Ground absorption. Once raindrops reach the Earth's surface, they can either be absorbed into the soil, flow into rivers and streams, or accumulate in surface water bodies like lakes. Some of the rainwater can also evaporate back into the atmosphere, continuing the cycle. The rain cycle is a continuous and natural process that plays a crucial role in providing freshwater resources for various ecosystems, agriculture, and human consumption. It helps maintain a balance in the Earth's climate and is essential for the survival of all living organisms. Hail is a type of precipitation that consists of hard, rounded ice pellets that can vary in size from small pellets to large, golf ball-sized chunks. Hailstones are formed in strong thunderstorms, known as supercells, where updrafts of air are powerful enough to keep ice particles aloft, allowing them to grow in size before falling to the ground. The process of hailstone formation involves several stages. 1. Updraft. In a severe thunderstorm, strong updrafts of air can lift raindrops into extremely cold regions of the storm's cloud, called the anvil. These updrafts can reach speeds of over 100 miles per hour, 160 kilometers per hour. 2. Supercooling. The raindrops that are carried into the extremely cold upper regions of the cloud can supercool, meaning they remain in liquid form even though they are well below the freezing point. 3. Ice nucleation. Supercooled water droplets come into contact with ice nuclei, tiny particles of ice, dust, or other solid materials. When this contact occurs, the supercooled water rapidly freezes onto the ice nuclei. 4. Layering. As the hailstone is lifted by the updrafts, it encounters liquid water and supercooled water droplets in the cloud. The supercooled water freezes onto the hailstone's surface, causing it to grow larger and creating layers of ice. 5. Pellet formation. Hailstones are built up through multiple trips into the updrafts and downward through the supercooled cloud regions. Each time they go through the supercooled regions, they acquire additional layers of ice. 6. Hailstones fall. Eventually, hailstones become too heavy for the updrafts to support, and they fall to the ground. The size of the hailstones depends on the strength and duration of the updrafts and the amount of supercooled water available for freezing. Hailstorms can cause significant damage to crops, buildings, and vehicles. The size and frequency of hailstones vary by region and are most common in areas with frequent thunderstorms. Scientists continue to study hail formation and develop methods to mitigate hail-related damage, but predicting the exact size and impact of a hailstorm remains a challenge. Precipitation is a meteorological term that refers to any form of water, liquid or solid, that falls from the atmosphere to the Earth's surface. There are several types of precipitation, each with its own unique formation process. The main types of precipitation are rain, snow, sleet, and hail. Here's how each of these types forms. 1. Rain. Raindrops form through a process called condensation and coalescence. It begins when warm, moist air rises and cools as it ascends. As the air cools, it cannot hold as much moisture, so water vapor condenses into tiny water droplets. These water droplets continue to grow as they collide with one another and combine. Once they reach a sufficient size, they fall to the ground as rain. 2. Snow. Snowflakes form when water vapor in the atmosphere crystallizes into ice. This process is called deposition. Snowflakes can take on a variety of intricate and unique shapes, depending on temperature and humidity conditions in the cloud. When snowflakes accumulate and bond together, they create snow, which falls to the ground as a solid form of precipitation. 3. Sleet. Sleet occurs when raindrops freeze into ice pellets before reaching the ground. This process typically happens when a layer of freezing air is present above the ground, causing raindrops to freeze as they pass through it. The resulting ice pellets fall to the ground and often create hazardous driving conditions. 4. Hail. Hailstones are formed in severe thunderstorms where strong updrafts of air can carry raindrops into extremely cold regions of the storm's cloud. Inside the cloud, supercooled water droplets freeze onto ice nuclei, creating the initial hailstone. The hailstone grows as it is lifted and descends multiple times through the supercooled cloud regions, acquiring additional layers of ice with each trip. When hailstones become too heavy for the storm's updrafts to support, they fall to the ground. The type of precipitation that occurs depends on the temperature profile throughout the atmosphere. Rain typically falls from clouds with temperatures above freezing, while snow forms in colder conditions. Sleet and hail both involve freezing temperatures, but they differ in their formation processes and characteristics. Other less common types of precipitation include freezing rain, rain that freezes upon contact with cold surfaces, and drizzle, fine, light raindrops. The type of precipitation observed in a particular region is influenced by various meteorological factors, such as temperature, humidity, and air masses. Convectional precipitation is a type of rainfall that occurs as a result of atmospheric convection. Convection is the vertical movement of air masses in the atmosphere, typically caused by the heating of the Earth's surface. Convectional precipitation is common in areas with a warm climate and is often associated with thunderstorms. Here's how convectional precipitation forms. 1. Solar heating. During the day, the sun's energy heats the Earth's surface, especially in tropical or subtropical regions. This heating causes the air near the surface to become warm and less dense. 2. Rising warm air. As the warm air rises, it cools and condenses at higher altitudes. When warm, moist air rises, it can carry water vapor with it. As the air cools, the moisture in the air condenses into water droplets or ice crystals. 3. Formation of cumulonimbus clouds. The rising, moist air forms cumulonimbus clouds, which are towering and often associated with thunderstorms. These clouds have strong updrafts and downdrafts. 4. Precipitation. Inside cumulonimbus clouds, the updrafts can carry water droplets high into the cloud, allowing them to freeze. This process results in the formation of ice pellets. When these ice pellets grow heavy enough, they fall to the ground as precipitation. Convectional precipitation is characterized by intense, localized rainfall with a short duration. It often occurs during warm afternoons or evenings when the ground is heated by the sun. Thunderstorms can be associated with convectional precipitation, and heavy rainfall can lead to localized flooding. This type of precipitation is common in regions with a tropical or subtropical climate, as well as in areas with strong daytime heating, such as deserts. Convectional precipitation plays a crucial role in replenishing groundwater and supporting vegetation in many parts of the world. Orographic precipitation, also known as relief precipitation or mountain precipitation, is a type of rainfall that occurs when moist air is forced to rise over elevated terrain such as mountains. As the air ascends over the mountains, it cools, condenses, and forms clouds, resulting in precipitation. Orographic precipitation is a common meteorological phenomenon, especially in regions with significant mountain ranges. Here's how orographic precipitation forms. 1. Moist air approaches mountains. Orographic precipitation begins with the arrival of moist air masses. This moist air is often laden with water vapor, and it approaches a mountain range. 2. Orographic lifting. As the moist air encounters the mountain range, it is forced to ascend due to the physical barrier presented by the mountains. This ascent is called orographic lifting. The air rises along the windward side of the mountains. 3. Cooling and condensation. As the air rises, it undergoes adiabatic cooling. The air temperature drops with increasing altitude, and when the dew point temperature is reached, water vapor in the air condenses to form cloud droplets. These clouds are often thick and persistent. 4. Precipitation. With continued ascent, the cloud droplets grow and coalesce into larger water droplets. Eventually, the droplets become heavy enough to fall to the ground as precipitation. Orographic precipitation can take the form of rain, snow, or other forms of precipitation depending on temperature and altitude. 5. Rain shadow. On the leeward side, downwind side, of the mountains, the descending air is now drier and warmer. This creates a rain shadow effect, where the air is often devoid of moisture. As a result, the leeward side of the mountains receives much less precipitation, and it can be significantly drier. Orographic precipitation is a crucial water source for many regions with mountainous terrain. It supports ecosystems, agriculture, and freshwater resources. Regions with prominent mountain ranges, such as the western United States, for example, the Sierra Nevada and the Rocky Mountains, and the western coast of South America, Andes Mountains, experience orographic precipitation patterns. These regions often have wet windward slopes and arid rain shadows, showcasing the significant impact of orography on local climates. Cyclonic, or frontal precipitation, occurs in association with the passage of a front, which is a boundary between two air masses with different temperature, humidity, and density characteristics. This type of precipitation is common in mid-latitude regions and is often associated with the formation of low-pressure systems and frontal boundaries. Cyclonic precipitation can result in various forms of precipitation, including rain, snow, sleet, and hail. Here's how cyclonic precipitation forms. 1. Frontal boundaries. Cyclonic precipitation is closely linked to the presence of frontal boundaries, particularly warm fronts and cold fronts. These fronts are the transition zones between two contrasting air masses. 2. Frontal lifting. When a warm front approaches a cold front, the less dense, warmer air is forced to rise over the denser, cooler air. Similarly, a cold front advancing under a warm front may force the warmer air to rise over it. This process is known as frontal lifting. 3. Cloud formation. As the warm, moist air is lifted over the cold front, it cools adiabatically. Cooling leads to the condensation of water vapor, and clouds form. Depending on the temperature and altitude, these clouds can be stratiform clouds, such as altostratus and nimbostratus, which are associated with continuous, light to moderate rain. 4. Precipitation. In the vicinity of the front, the lifted air may continue to cool and condense, leading to the formation of precipitation. The type of precipitation, rain, snow, sleet, or hail, depends on the temperature profile of the atmosphere. 5. Frontal movement. As the front continues to advance, it carries the area of precipitation with it. Cyclonic, frontal, precipitation can be widespread and may last for an extended period as the front moves across a region. 6. Weather conditions. Depending on the interaction of the warm and cold air masses, cyclonic systems can produce a variety of weather conditions, including steady, prolonged rainfall or snowfall, sometimes accompanied by thunderstorms and severe weather. Cyclonic precipitation plays a crucial role in the distribution of precipitation in mid-latitude regions and is responsible for many weather-related phenomena, such as heavy rainfall events, snowstorms, and the replenishment of water resources. It is a common feature in the weather patterns of regions affected by mid-latitude cyclones, including parts of North America, Europe, and Asia. Wind is the movement of air in the Earth's atmosphere. It is caused by the uneven heating of the Earth's surface by the sun, which creates differences in air pressure. As air flows from areas of high pressure to areas of low pressure, it generates wind. Here are some key points about wind. 1. Causes of wind. Wind is primarily caused by the uneven heating of the Earth's surface. During the day, land heats up more quickly than water, creating areas of low pressure over the warm land. Over cooler bodies of water, there is higher pressure due to the slower heating. Air moves from the high pressure areas, for example, oceans, to low pressure areas, for example, land, creating wind. 2. Direction of wind. Wind direction is described by the direction from which the wind is coming. For example, a north wind blows from the north to the south. Wind direction is typically reported using cardinal directions, for example, north, south, east, west, or in degrees from true north. 3. Wind speed. Wind speed is measured in units such as meters per second, meter per second, kilometers per hour, kilometer per hour, or miles per hour, mile per hour. The wind speed can vary from gentle breezes to strong gales or storms. 4. Local wind patterns. Local geography and weather patterns can influence wind. For example, coastal areas often experience sea breezes, where cool air from the ocean moves inland during the day, and land breezes, where warmer air from the land moves seaward at night. 5. Global wind patterns. On a global scale, there are specific wind patterns due to the rotation of the Earth. These include the trade winds, westerlies, and polar easterlies. These wind patterns play a crucial role in weather and climate systems worldwide. 6. Wind as a resource. Wind can be harnessed as a source of renewable energy through wind turbines. Wind energy is a clean and sustainable source of power used for electricity generation. 7. Effects of wind. Wind can have various effects, including shaping landscapes, for example, sand dunes, transporting seeds and pollen, influencing weather patterns, and even causing damage during severe storms, such as hurricanes, tornadoes, and typhoons. 8. Measuring wind. Wind speed and direction are typically measured using instruments called anemometers and wind vanes. Modern technology has led to more sophisticated methods of measuring and monitoring wind, including radar and satellite observations. Wind is a fundamental element of the Earth's climate and plays a critical role in the distribution of heat and moisture around the planet. Understanding wind patterns is essential for meteorologists, sailors, and many other fields related to weather, climate, and environmental science. Turkey's climate is diverse due to its unique geographic location at the crossroads of Europe and Asia, its varied topography, and its proximity to both the Mediterranean Sea and the Black Sea. Here are the main climate zones and characteristics of Turkey. 1. Mediterranean climate, south and west. The coastal regions along the Mediterranean and Aegean seas, including cities like Antalya, Izmir, and Bodrum, have a Mediterranean climate. This means hot, dry summers and mild, wet winters. Summers are generally sunny and hot, with temperatures often exceeding 30 degrees Celsius, 86 degrees Fahrenheit. Winters are mild and wet, with temperatures rarely dropping below freezing. 2. Aegean climate, west. Similar to the Mediterranean climate, the Aegean region experiences hot, dry summers and mild, wet winters. However, it can be slightly milder and wetter than the Mediterranean coast. 3. Continental climate, central Anatolia. In the central part of Turkey, including the capital city Ankara, a continental climate prevails. This means hot, dry summers with temperatures often exceeding 30 degrees Celsius, 86 degrees Fahrenheit, and cold, snowy winters with temperatures well below freezing. Temperature variations between summer and winter are more pronounced in this region. 4. Black Sea climate, north. The Black Sea region, including cities like Trabzon and Rize, has a maritime climate. It is characterized by mild, wet summers and cool, rainy winters. This area receives a significant amount of rainfall, especially during the winter months, making it lush and green. 5. Eastern Anatolia, east. Eastern Anatolia has a more pronounced continental climate. Summers are warm, but winters are extremely cold, with heavy snowfall. Cities like Erzurum and Van experience sub-zero temperatures in the winter. 6. Southeastern Anatolia, southeast. The southeastern region, including cities like Diyarbakir and Gaziantep, has a semi-arid climate. Summers are hot and dry, while winters are mild and dry, with very little rainfall. 7. Mountain climates. High mountainous areas, such as the Taurus and Pontic Mountains, experience alpine climates with cold temperatures, heavy snowfall in winter, and mild summers. 8. Coastal areas. Coastal areas are generally milder and more temperate, thanks to the mitigating influence of the sea. 9. Rainfall. Turkey's climate exhibits diverse rainfall patterns. The western coastal regions receive more rainfall, while the central and eastern parts of the country are drier, especially in the summer. The eastern Black Sea coast is one of the wettest regions in Turkey. 10. Wind patterns. Turkey's climate is influenced by various wind patterns, including sea breezes along the coasts, which bring cooling effects during the summer. The average annual rainfall in Turkey is approximately 640 mm, with the majority occurring during the fall and winter seasons. Rain is the predominant form of precipitation. Conversely, summer experiences the least amount of rainfall, accounting for roughly 10% of the total annual precipitation. Turkey exhibits notable variations in monthly rainfall distribution across different regions and seasons. For instance, the eastern Black Sea coasts, known for the highest recorded rainfall, receive consistent rainfall throughout the year, totaling around 2,000 mm annually. In contrast, inland areas with annual average rainfall below 300 mm in some regions along the Mediterranean coast experience minimal rainfall during the summer months. These disparities underscore the significant differences in precipitation patterns within the country. During the winter months, the influence of the Azores and Basra systems weakens and shifts southward. As a result, polar air masses and low-pressure systems from Iceland and the Mediterranean become the primary factors influencing weather patterns in Turkey. The Icelandic low-pressure system is the most significant source of winter precipitation in Turkey, often associated with the formation of fronts that bring substantial rainfall. Additionally, the interaction between humid, mild air from the Mediterranean and cold air systems from the north generates significant rainfall, particularly along the Mediterranean coasts. Rainfall during this period is more pronounced along the Black Sea coast. Systems approaching from the north and northwest typically begin as rain on the coastal areas and transition into snowfall as they move inland. Conversely, systems coming from the south and southwest impact Anatolia, resulting in rain along the coasts and snowfall in the inland and higher regions. In areas heavily influenced by the Siberian high-pressure system, a terrestrial air mass of polar origin, dry and extremely cold frosts occur, leading to the lowest temperatures of the year. Summer conditions. During the summer in Turkey, the influence of southern air masses is dominant, driving various weather-related events. In this period, the high-pressure system of the Azores also extends its impact to Anatolia and contributes to precipitation along the Black Sea coasts when the Basra low-pressure system is less active. These northern air masses are responsible for the prevailing winds during this season. However, the most significant feature of the summer period is the pronounced influence of the Basra low-pressure system, which originates from the south and is of tropical air mass origin. This predominantly dry and hot air mass, coming from the southeast, has a substantial effect on the region. As the effect of frontal systems, which can bring precipitation, diminishes during the summer, there is minimal rainfall in regions outside the Black Sea coast. Instead, orographic and convectional precipitation become prominent characteristics of this season, particularly in the inner regions. The Köppen climate classification system is widely used to categorize and describe various climate types based on temperature and precipitation patterns. In Turkey, the Köppen classification system is applied to identify the different climate regions. Here are some of the primary Köppen climate types found in Turkey. 1. Mediterranean climate, KSA, CSB. This climate is prevalent along the southern and western coasts of Turkey, including regions like Antalya, Mersin, and the Aegean and Mediterranean coasts. It is characterized by hot, dry summers and mild, wet winters. Summers are generally dry, and the majority of the rainfall occurs during the winter months. 2. Black Sea climate, CFA, CFB. The Black Sea region, including cities like Trabzon and Rize, features this climate type. It is known for its high levels of precipitation throughout the year, with mild and wet winters and cooler, relatively drier summers. The Black Sea coast receives abundant rainfall due to its proximity to the sea and orographic effects. 3. Continental climate, DSA, DSB, TKA. This climate is found in the interior parts of Anatolia, away from coastal influences. Cities like Ankara and Kayseri experience this climate. It is characterized by hot and dry summers, as well as cold and snowy winters. There is a significant temperature difference between summer and winter. 4. Steppe climate, BSK, BSK, BSH. The steppes in southeastern Turkey, including regions near Gaziantep and Sanliurfa, feature this type. It is characterized by hot summers and cooler, relatively dry winters. Precipitation is generally low, leading to arid conditions in some areas. 5. Cold desert climate, BWK. Parts of eastern and southeastern Turkey, such as Sırnak and Hakkari, fall under this category. It is characterized by extremely hot summers and cold, dry winters. Precipitation is minimal, and the region exhibits arid to semi-arid conditions. 6. Alpine climate, ET. High mountain areas in eastern Turkey, including regions near Erzurum and Kars, feature this type. It is characterized by cold temperatures throughout the year, with snowfall in the winter. Precipitation varies depending on the location and elevation. 7. Subarctic climate, DFC, DWC. The Kars Plateau in northeastern Turkey experiences a subarctic climate, with cold winters and short, cool summers. These are some of the primary Köppen climate classifications found in different regions of Turkey. The country's diverse geography and topography contribute to a wide range of climate types, making Turkey a climatically diverse and geographically interesting place. The Black Sea climate predominantly influences the Black Sea coastal areas and the north-facing slopes of mountains. There are minimal temperature variations between seasons. Summers tend to be relatively cool and humid, while winters along the coast are mild, but they become progressively warmer as you move to higher altitudes. The climate is characterized by consistent rainfall throughout the year, though there are variations in recorded precipitation and temperature values in the western, central, and eastern regions. On average, the annual precipitation is 850 mm, with around 600 mm in the central Black Sea coast and approximately 2,000 mm in the eastern parts. The abundant rainfall has fostered a lush and diverse natural vegetation pattern corresponding to different altitude levels. This climate type is marked by mild conditions, with annual average temperatures that do not drop into negative values. January experiences an average temperature of 4.2 degrees Celsius, while July reaches 22.1 degrees Celsius, resulting in an annual average temperature of 13.0 degrees Celsius. The Mediterranean climate influences several parts of Turkey, including the coastal regions of Marmara, the Aegean, and the Mediterranean, as well as the mountainous areas adjacent to these coasts. In particular, the Taurus Mountains play a role in restricting this climate from penetrating further inland, although it can extend more widely along the Aegean coasts. Summers in these regions are characterized by hot and dry conditions, while winters are typically warm and rainy. Coastal areas rarely experience snowfall and frost, but higher elevations in the mountains have snowy and cold winters. In this climate type, the average temperature in January is 6.4 degrees Celsius, rising to 26.8 degrees Celsius in July, with an annual average temperature of 16.3 degrees Celsius. The area under the Mediterranean climate receives an average annual precipitation of 725 mm, with a significant portion occurring during the winter months. Recorded precipitation is notably low during the summer period, accounting for just 5% of the total annual precipitation. The natural vegetation in the Aegean and Mediterranean coastal zones consists of red pine and maquis elements. Due to changing climatic conditions in higher elevations, coniferous trees, especially conifers, become more prevalent. In Turkey, the inner regions are primarily dominated by a continental climate, with some variations between different areas. This climate type is observed in central Anatolia, eastern Anatolia, southeastern Anatolia, and Thrace, and it exhibits significant differences, particularly in terms of temperature. Typically, the continental climate is characterized by hot and dry summers, except for eastern Anatolia, which receives summer precipitation, and spring is the rainy season in many areas. Winters tend to be cold and snowy, with eastern Anatolia experiencing the harshest winters. This region is known for its very low temperatures and long-lasting snow cover, often exceeding 180 days, making it one of the coldest parts of Turkey. In southeastern Anatolia, the continental climate transitions into a Mediterranean climate, especially in the western parts of the region. However, in the eastern areas, the continental influence remains more pronounced, leading to cold winters. Precipitation varies across different regions influenced by the continental climate. In central Anatolia, the average annual precipitation is around 300 to 400 mm. In eastern Anatolia and southeastern Anatolia, it ranges from 500 to 600 mm, and Thrace, which experiences a continental climate, receives approximately 400 to 700 mm of annual precipitation. The mountain climate in Turkey, which primarily affects high and mountainous regions, is characterized by significant variations in temperature and conditions over short distances. For instance, the climatic conditions in the mountainous areas near the eastern Black Sea and Mediterranean coasts differ greatly from the coastal regions below. These mountainous regions experience large daily temperature variations and exhibit variations in climate elements like precipitation, cloud cover, and wind patterns. The distribution of these climatic elements, especially rainfall, varies significantly between the two sides of the mountains due to differences in topography. The mountainous areas, whether they are part of coastal fold mountains or high volcanic mountains in the interior regions, are vital water resources for the surrounding areas because of their snow and glacial resources.